Hi, and welcome to part 9 of my series of videos about the best methods for alkylating carbon nucleophiles. This presentation is about the Friedel-Crafts alkylation of arenes. Neutral arenes are weak nucleophiles and usually only react with cationic electrophiles, mostly under acidic conditions. Typical Friedel-Crafts alkylations proceed by intermediate formation of cyclohexadienyl cations, and the regioselectivity is determined by the precise location of carbocation stabilizing or destabilizing groups, like in the Friedel-Crafts acylation. You may check my video about Friedel-Crafts acylations for an overview of the effect of various types of substituents on aromatic electrophilic substitutions. Because alkyl groups enhance the reactivity of arenes toward electrophiles about 20-fold, the inherent problem of Friedel-Crafts alkylations is that the product is more reactive than the starting arene, and multiple alkylations can easily occur. Suitable electrophiles for the alkylation of arenes include alcohols, alkyl halides, sulfonates, epoxides, but also alkenes. For large-scale preparations, alkenes are the most important electrophiles used, because these alkylations do not generate any waste or potential catalyst poisons. Alcohols are not as convenient as alkenes, because water deactivates most of the required catalysts. Depending on whether the olefin is electron deficient or electron rich, primary or secondary alkyl arenes can result from such alkylation reactions. Aldehydes and ketones can also be used as electrophiles, but instead of benzylic alcohols, diaryl methanes are usually obtained. The intermediate benzylic alcohols form carbocations too readily, so that a benzylation of the starting arene is almost impossible to prevent, unless the aldehyde or ketone contains strongly electron-withdrawing, carbocation-destabilizing groups. The conversion of aldehydes into secondary alcohols was already discussed in another playlist. A second group of arene alkylations proceeds by intermediate transition metal chelate formation. A number of functional groups promote orthometallation, often without the need of strong bases. The resulting chelate can react with electrophiles such as alkyl halides or olefins to the corresponding alkylated or olefinated arenes. Also, polar organometallics may be prepared this way, for instance lithiated arenes, and the reactions were discussed in the first 2 videos of this playlist. These here are some suitable starting materials for this kind of chemistry. Because of the structural requirements for the starting arene, the scope of chelate-mediated reactions is quite narrow. Also, heteroarenes can sometimes be alkylated. Under Friedel-Crafts conditions, a higher electron density at the arene usually facilitates electrophilic substitutions, but also increases the risk of acid-catalyzed oligomerization. The most electron-rich heteroarenes are pyrols, furanes, thiophenes, and their benzoannulated relatives. Amino, hydroxy or alkoxy pyrols or thiophenes are even more electron-rich and are difficult to isolate and usually polymerize in the presence of air or acids. Thiazoles are similarly reactive as donor-substituted arenes, while imidazoles and pyrazoles are rather unreactive at carbon. Imidazoles are among the most stable heterocycles and can be heated to over 500 degrees Celsius without decomposition. N-alkyl imidazoles can actually be lithiated by treatment with butyl lithium, what also indicates that imidazole is more electron deficient than benzene. Finally, pyridines and diazenes are even more electron deficient and do not usually react with electrophiles at carbon. The advantages of the direct electrophilic alkylation of arenes is the good availability and low cost of the starting materials. And once suitable conditions have been found, these reactions are also easy to perform and are often used for large-scale commercial preparations. Here are some examples of large-scale acid-catalyzed arene alkylations. One route for the production of styrene is the dehydrogenation of ethylbenzene, which is prepared from benzene and ethylene. Alkylation of benzene with propene yields cumene, which is oxidized by air to cumene hydroperoxide and then fragmented into phenol and acetone. Phenols are easy to alkylate, for instance to methylphenols by treatment with methanol or to bisphenol A by acid-catalyzed condensation with acetone. The main disadvantages of electrophilic arene alkylations are that multiple alkylations can be difficult to suppress and that a large number of side reactions might occur. I'll show you some of these later. Often, the direct electrophilic alkylation of arenes is not the best way to prepare a given alkyl arene. There are some alternatives that may look more tedious at first glance but can turn out to be superior. One alternative strategy is Friedel-Crafts acylation followed by reduction. Because the intermediate aryl ketones are electron deficient, Friedel-Crafts acylations usually only occur once, and the ketones are obtained in high yield and often with predictable and high regioselectivity. Then, aryl ketones can be reduced by a number of different methods, such as the Wolff-Kishner reduction with hydrazine and a base, or by the Clemenson reduction with zinc and hydrochloric acid, or by catalytic hydrogenation. For expensive products, silanes in the presence of acids can also be used as reducing agent. One further alternative to the electrophilic alkylation of a neutral arene is metallation followed by electrophilic alkylation. Some arenes, such as polyhaloarenes or alkoxyarenes, can be converted into aryl lithium or aryl sodium compounds by treatment with strong bases. These metallated arenes are highly reactive and easy to alkylate with a broad selection of electrophiles, such as alkyl halides or alkenes. If aldehydes or ketones are used as electrophiles, in this case no diaryl methanes are formed, because the resulting benzylic alcohols are stable under basic reaction conditions. Most benzylic alcohols are easy to reduce to alkanes, for instance by catalytic hydrogenation or by treatment with acids and some hydride donor. This is a beautiful example of multiple Friedel-Crafts alkylations. In the first step, benzene was ethylated 3 times by treatment with ethyl bromide and aluminum chloride. Interestingly, mainly one regioisomer was obtained. In a second step, this intermediate was bromomethylated 3 times by treatment with formaldehyde and hydrogen bromide under forcing conditions. Again, mainly one isomer was formed. This good result is not typical, because di- and trialkyl benzenes readily isomerize in the presence of acids and often yield large numbers of isomers. Friedel-Crafts alkylations with haloacetic acid derivatives or other polyelectrophiles do not always proceed as expected. One possible reason being that alpha-acyl carbocations are destabilized and difficult to generate. In this example, the authors succeeded, however, to alkylate benzene with a lactic acid-derived mesylate. The 2 potential side reactions, namely methylation or acylation of benzene, did not occur to a large extent. With chloroacetonitrile, however, no cyanomethylation but acylation is usually observed, as in this example. Also lactones may act as acylating or alkylating reagents. In this example, butyrolactone, in the presence of an excess of aluminum chloride, acted mostly as an alkylating reagent. Allylic electrophiles can yield 2 regioisomers, and it is not always easy to predict what product will be formed. In this example, the alpha-trifluoromethyl cation is more reactive, but probably does not contribute to the real structure of the allylic cation as much as the benzylic cation. Upon reaction with benzene, mostly benzylation occurred. This is the optimized procedure for an intramolecular electrophilic alkylation of a dialkyl benzene with a primary alcohol. As catalyst, an acidic ion exchange resin was used, and a high yield of the required substituted tetraline was obtained. The main side reaction was aromatization by twofold dehydrogenation, despite the absence of transition metal catalysts. This result was far from obvious, because primary carbocations quickly rearrange to secondary carbocations by hydride migration, and 5-membered rings are usually formed much faster than 6-membered rings. So the authors were lucky that in this instance tetraline formation was faster than indane formation. When arenes are alkylated by simple terminal olefins, secondary alkyl arenes usually result. As in this example, the secondary carbocation may even migrate to other positions and cause the formation of product mixtures. In this instance, no strong acid, but only 1% of a nickel-2 imide and an ionic liquid were used as catalysts. The excess benzene was necessary to prevent the formation of dialkylated benzenes. This is an interesting example of chelate-mediated alkylation of a benzoic acid. These are electron deficient and usually require strongly acidic reaction conditions to be alkylated or acylated. With palladium-2 salts, however, benzoic acids form orthometallated chelates under mild conditions that react both with alkylating reagents or with olefins. In this example, an epoxide was used as alkylating reagent and a high yield of lactone was obtained. Let's have a look at potential side reactions. As already shown, carbocations readily rearrange by hydride or alkyl group migration, in particular primary carbocations. In this example, such a primary carbocation was generated by fluoride abstraction, but despite the high reactivity of this primary cation, rearrangement to a secondary carbocation was faster than the alkylation of benzene. Fluoride was abstracted preferentially because boron trifluoride binds more strongly to fluoride than to bromide. Hydride migration may also occur intermolecularly, as shown here. Instead of alkylating benzene, the chlorohexane-derived carbocation was reduced by hydride transfer from isopentane, whereby various isomeric pentyl cations were formed. Only 6% of hexyl benzenes resulted. Interestingly, not only terz amylbenzene was formed, that is, the product resulting from the most stable carbocation, but mostly other isomeric pentyl benzenes were obtained. In the presence of interconverting isomeric carbocations, the product distribution depends not only on the relative concentrations of the various carbocations, but to a large extent also on their reactivity. The latter is determined by the electronic stabilization of each cation, that is, the less stable the more reactive, and by the steric accessibility of each carbocation. Polyalkylarenes can isomerize under surprisingly mild reaction conditions, and one problem of Friedel-Crafts alkylations is the formation of isomeric mixtures. Then, allylic electrophiles can readily lead to the formation of indanes, as shown here. Despite the use of only 5% of a copper catalyst in dichloromethane, both an indane was formed and a methyl group migrated. Further potential side reactions include multiple alkylations. Electron-rich arenes, such as for instance phenols, may even be over-alkylated and de-aromatized. Finally, electron-rich arenes or heteroarenes are acid-sensitive compounds that readily oligomerize in the presence of strong acids. In particular, thiophenes and related heterocycles show this behavior, but even benzene or naphthalene oligomerize upon treatment with aluminum chloride in the so-called Scholl reaction. On this slide, there are some more recent examples of arene alkylations by alkyl halides, epoxides and related electrophiles, and by aldehydes. Many examples of the alkylation of arenes through intermediate chelate formation have recently been published, and here is a short selection. Finally, on this slide you have some more examples of alkylations by alkenes, by radicals and by carbenes, as well as some review articles. Many more examples have been published though, but with the examples I showed you, the scope of this reaction should be more or less clear.